Hello everyone and welcome back to this next lecture in the machines series. And in the past lecture we had actually created a very basic circuit of just a voltage source or a single phase AC voltage source feeding a resistor and inductor. And we had shown how just this very basic circuit can be made in one way to represent some kind of a load, which could be a machine, which is being connected or supplied by an AC voltage. Right? And we saw that when we simulate such a circuit, we do end up getting currents. And if you do adjust the resistance and inductance to certain values, this current can be close to what we want as a particular load. Now, the only problem with this particular simulation was that we are choosing a fixed resistance and a fixed inductance, which means you have one fixed load which is being connected to an AC supply. You have no control over it. Right? Now, to introduce control in this lecture, we are going to start bringing in controllable elements. We are still not going into the final solution because I want to go gradually into it. So before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you want something a little more comprehensive, I have a full-length video series, or rather full-length courses on the MOOC website Udemy, which you can check out. And here I'll show you. This is my website, which is pythonpowerelectronics.com. And in this website, if you go over to learn, you will see that these are the courses which I have so far. So there are many courses. For example, the very first one, which is called Simulating Power Electronic Circuits Using Python, is just to describe how you can simulate circuits with Python. And I talk about the installation of Python Power Electronics and how to use Python Power Electronics with some basic circuits. If you're interested more on the signal processing side, I have another course which is the basics of digital signal processing for power engineers, in which I talk about how you can design filters using Python. The next course is Simulation of Magnetics for Power Electronics using Python, in which I talk about how you can use Python Power Electronics to simulate inductors, coupled inductors, and transformers using Python Power Electronics. The next course which I have is Control Analysis with Python for Grid Connected Converters, in which I talk about the basics of control systems, specifically with the case of a single phase converter connected to a single phase grid. And the very latest course which I have is rather a free course called Why Specialize in Power Electronics, which talks about some of the advantages or some of the opportunities and challenges available in the power electronics domain. So this is mainly for junior undergraduates or even maybe high school students in case they are wondering which specialization they should choose. So the link for this link will be provided in the description for this video. If you're interested, do check it out. So anyway, let's come back to the lecture. So now that we have this, as I said, the next step is we are going to bring in some amount of control into our circuit. So what that means is I'm going to replace these two elements with controllable elements. So what that means is instead of having just a resistor, we are going to have a variable resistor. And similarly, there'll be a variable inductor. Right? Let me save it and let's go back. And as always, as I said, since you made a topological change, we must go back to the add circuit file and we must click on process circuit schematics. Right? Any topological change, which means a change in the actual circuit, a new branch added or a branch moved or elements changed in such a manner, always click on process circuit schematics. So main thing is it tells you there are no errors, so that's okay. Also, it creates Python objects for each and every circuit element. So let's go to edit circuit parameters and click on view components. So we now see there are now components for variable inductor and variable resistor. So this is what we had come up with. So all we have to do is we have to make a few changes. So this is the variable inductor. Now the variable inductor has an initial value which is 0.001. That's perfectly okay. But it has a control tag. Now this control tag is actually a future feature and it's not something that's used currently, but still it's a good idea to change it accordingly. So for example, I would call this load inductance. Just give it any name which is preferably unique corresponding to your circuit. So for example, since this is a load inductance, let's call it a load inductance. If it is in some cases, let's say a transformer leakage inductance, Let's call it a transformer leakage inductance. So this is save parameters, and then let's click on variable resistor. And here again, the initial value of the resistor is 100 ohms. That's perfectly okay. Let's however change this control tag to be load resistance, right? And save the parameters. So we now have two controllable components in our circuit. So what that means is we can now write a control file. So to write a control file, we have to now add, of course, the control file, which is a Python file. So let's go over to our editor, which is Atom. Now you can choose Atom or you can choose anything else. Now the directory which I currently have is the energy series directory. So I'll remove this and let me add another folder. And this folder is now our latest folder, which is machine series. So let's click on simulations. These are all the simulations. So we have only one simulation so far. So let me now add a new file and I will call this, I guess you can change load variation.py, right? It has to be a Python file. That's most important. So let's go over to our web browser and let us add this file. Let's go to machine series, simulation, simple RL load, and let's pick out load variation.py. And let's click out, what do I call this? I will call this setting load parameters and save the file. So now we have this configuration, which is configure control. Now, how would I do this? The simplest thing which I need to do here is all I have to do is I have to set the value for this variable resistor and variable inductor. This is what I have to do in simplest terms, right? So without much ado, all we have to do is we can add two control outputs. Each control output will be connected to one of these controllable elements. And by setting the value of these, we are now providing a value for this variable resistance and variable inductance. So let's do that. This is the simplest form of having a control file where we are editing the parameters of a circuit. So let's add control output. So variable inductor load, let's call this load inductance. Let's put a underscore in between. The initial value of the resistance or other initial value of the inductance can be, let's say, 0.001, just like we have in the parameters. And let's add another control output. This is the variable resistance. So we'll call this load resistance. And the value can be 100 ohms, just the way we had it for our parameters. Now, just this is enough, because remember, there is an initial value, right? So if we run the simulation, it will work, but it will work with these parameters, which we don't really want. What we need to do is we need to set these parameters in our control file. So let me copy it, go over to my editor, paste it, copy the other one as well, back to my editor, paste it. So if I set these two values, and let me just put a little comment here saying load parameters. If I set this value to be, let's say 0.3 and let's say 10, right? The reason I'm choosing 0.3 is because if I say 2 into pi into 50 into 0.3, this is 100 into pi into 0.3, right? Now 100 into pi would be around 314.1 multiplied by 0.3 is, I would say, is around 100, right? So we have 100 ohm resistance due to the inductance. So therefore, let's put 75 ohms of resistance and 100 ohms of inductance. So this is a load that is actually drawing a huge amount of reactive power because the inductance is larger than the resistance. So the power factor of this load is quite poor, right? Now this of course depends upon the nature of load that we want to simulate. If we are simulating an induction motor or some kind of motor working at very poor power factor, this might be a reasonable choice. So let's save this, and that's all we need, right? If we don't have a time event variable, this control file is running at the same speed as a simulation, right? So if we have chosen 1 microsecond for our simulation integration time step, this control file will be run every 1 microsecond when the simulator solves the equations, right? Later on, we will add other parameters so that we can solve this at our own time speed, or rather our own time step. So with this, we are good to go. Let's go back to the main page and let's go back to view output, right? Now let me go to my file browser and let me just rename these files. Actually, I don't need to rename because I don't need it. So now that we're here, let's go and run the simulation. So let's click on the run button. Simulation is running, but always go to the command line, make sure there is no error, right? That means the simulation is actually running. So let's go to the Google Chrome, click on the plot buttons, the voltage and the current. So these are our currents and voltage, right? So you see we have a current and we have a voltage, right? Now of course, since we have a current of 3 amperes and a voltage of 300, we could plot them together if we scale the voltage down. So for example, if I come over here and add another plot, and let's call this power factor because that's what we are trying to do. We are trying to ascertain the power factor of the load. So the first waveform can be ammeter Vin. What was it before? It was ammeter Vin. So let's call this I. We don't need a scaling factor here. Save the waveform. And then let's plot the voltage. But here let me scale this down. And since our voltage is 300, let's scale it down by 0.01. That means we are taking only 1% of the voltage. So if I save these two, click on done. And now let's plot this power factor. So this will show us the power factor of the load. We might have to zoom in. And as you can see, we probably do have to zoom in. So let's zoom in between 0.2 and 0.3. And let's go to the file browser and let's look at this. And let's look at the power factor. So this is what we did. Now remember, because of the way we chose our resistance and inductance, the resistance and inductance is comparable, which means the inductance is actually larger than the resistance. The result is we will have a significant phase lag between the voltage and the current. So if you look at this, the orange or the yellow line is the voltage and the blue line is the current. So the current is lagging behind the voltage. And if we have a look even further, we'll see that this lag is significant. Typically this lag should be slightly more than 45 degrees because we have an inductance which is slightly greater than the resistance, right? So therefore, or I'm not sure which way you look at it, but whichever, it is because of the nature of this particular load, or rather this load, then the phase lag between the current and, or rather phase difference between the current and the voltage will be significant in the range of around 40 to 50 degrees, right? The exact value depends upon the actual values. Now we have now produced a control file with which we can set these values. Now what is the advantage of this? The advantage of this is now we can dynamically change our values. We can at some particular time increase or decrease our resistance and inductance, right? So we can change the values as and how we want them to. So just in case, let's go back. Let me stop this simulation. go back to the editor, and let's put that as well. So for example, we have load parameters. Why don't I put a time condition? So let's say I say if t clock is less than let's say 0.1, I have these values. If not, that is, as t clock is greater than 0.1, let's change them to some other value. So for example, if I come here, let me get rid of this comment. Now instead, let me choose a smaller value. So for example, let's say I make this 0.1. So which means now the inductance is much lesser than the resistance, because this is reduced around 30 ohms. So if it is reduced to 30 ohms, you would see a change in the value of this current. So let's go and run it again. Always go to the command line, make sure there is no error, there is none. So that means the simulation is running. So what we need to do, let's plot the current. Let's go to the file browser. And it will take some time to run, so that's okay. So this is our current. This is the current we had even before, because until 0.1 seconds, we have an inductance of 0.3 Henry and a resistance of 100 ohms. So this will change when we now go to around 0.1. So there's nothing much to do. We just have to wait and run it again. So let's run it. And we see the difference. So the reason I chose 0.1 so that we can get the simulation fairly quickly, we'll see that until 0.1 we have a particular current, and after that the current has increased. The reason why the current is increased is quite obviously because we have decreased the load inductance, which means the total load impedance has decreased, and therefore the current will increase. Right? Now, what is more interesting, or rather what is also interesting, would be to check out how the power factor is. How the power factor is before the change and after the change. So let me come over here, choose the power factor, and we can see the difference. So it is a little difficult to see it here. So let me zoom in between around 0.75 and 0.15, or rather I suppose 0.75. Yeah, that's good enough. So let me zoom in between 0.075 and 0.15. And let's go back here. Have a look. Yes, it is now quite clear. So you see, the voltage remains pretty much the same because our feeder impedance is so negligible that even if the current changes by such a small amount, the voltage drop across the load does not change that much, right? Which is why it's pretty much steady. The current, however, has changed significantly. Initially, the current until 0.1 seconds is much smaller because the load impedance is larger. When the load impedance decreases, then the load current increases, right? Now, however, you see not only has the magnitude changed, the phase angle has also changed. In the previous case, when the load inductance was 0.3 Henry, the phase angle difference was much more because the load inductance is larger. So the power factor of the load is poorer. After the transient, because we've decreased the load inductance, the power factor of the load improves and the phase angle difference between the voltage and the current has now decreased. This is how we have simulated a kind of load change, right? So we have now progressed from having a fixed inductance and a fixed resistance symbolizing a particular load to a variable resistance and a variable inductance, right? So now we can simulate changes in the load. So things like this we can simulate. For example, if you're simulating a simple load connected to a particular AC generator, you can use this and you can increase or decrease the values of resistance and inductance and therefore see the effect on the generator, right? In many cases, this is usually good enough, particularly when you're simulating, let's say, a power electronic converter, like a buck converter or a UPS. You would want some load. And of course, you would also have to introduce some kind of a load transient. So this is usually a very convenient way to introduce a load transient and to see how your power converter is working, right? This is very normal. But in our case, we want something a little more elaborate, because remember, we are trying to actually model a machine, an electrical machine, which means that we need to very, very specifically be able to generate a particular current, right? For example, when the machine starts up, it draws a certain kind of current. When the machine accelerates, it draws a certain kind of current. When a machine stops, it draws a certain kind of current, right? While it is stopping. So there is this behavior of the machine which, corresponding to its behavior, will draw a certain current. And that's what we want to simulate when we are actually modeling an electric machine. So even this resistance inductance basic simulation, by having variable resistance and variable inductance, though is okay in some cases like simulating a UPS or a power converter, for practical applications like actually simulating an electrical machine, we would need something even more intricate, where we have absolute control over this current, right? Here we are just guessing. We are just guessing a particular resistance, a particular inductance, and we are seeing the current. But this is not good enough when you want to simulate the machine itself. So with this, I'm going to end this lecture. In the next lecture, what we are going to look at is another way to represent a variable load. That is, in this case, we have represented a variable load as a variable resistance and a variable inductance. But there is one more way to do this. And that way is by choosing, instead of a variable resistance and a variable inductance, choosing a variable voltage in series with a variable resistance. That is what we are going to use next. And this is usually called as a voltage in series with a resistance, or a voltage in series with an impedance. Now, this method is what we will use going further when we want to model electrical machines. And we've already used it in the previous series when we were simulating transformers. In this series, we will use it for simulating electrical machines, rotating machines like induction machines, synchronous machines. So with this, I will end this lecture. If you have any doubts about what I did, feel free to message, either email me or send me a message on social media or post a comment in this video. Otherwise, next week we will continue with this to actually simulate a more detailed model of a voltage, or rather a more detailed model of a load that comes close to what we want to simulate when you want to simulate an electrical machine. So, thank you so much for listening and see you soon. Goodbye for now.